So the next talk would be given by Haim Beidenkopf from Weizmann Institute, and there is a change of title that we will
now I can apologize to everyone else. I will report our results on semiconducting nanowires, where, one moment, where we see new phenomena that we didn't know about before in semiconducting nanowires coming from interactions in these materials. Okay, and we'll be happy to talk privately about our weak TI measurements. So, of course, semiconducting nanowires have got a topological twist about 4 years ago, where 2 years before the notion of a Majorana wire, or topologically superconducting wire in one dimension, was suggested to be realized in these materials. And later, indeed, zero bias conductance peaks have been detected in Delft, and later on in Israel and in China and other places since. However, seeing that the Majorana wire is just a recent example of the fascinating physics that we get in one-dimensional electronic systems, there have been other interesting findings before, such as spin charge separation, charge fractionalization, and I will show you today two other phenomena that we see in these semiconducting nanowires. And generally, I think we don't yet understand enough the physics of electrons in these nanowires, definitely from the point of view of scanning tunneling microscopy or local spectroscopical tools. And this is mainly because of this thin layer that you can see already if I blow up this TEM image. This is an oxide layer that develops on the surface of the nanowires and does not allow local spectroscopies of these objects, and this is why they are almost absolutely absent from the literature. We tackle this problem kind of by brute force, simply by keeping our nanowires under UHV at all times, transferring them from the MBE to the STM system without breaking vacuum, which allowed us to study them in STM. We already saw a talk about STM before by Shikon Shu, so I won't spend much time on the technique, more on the physics that we find. So again, we bring a sharp metallic tip to the surface of the sample, and we can take the topography of our sample. And in this case, our sample is a gold substrate with two nanowires resting on it randomly in a T-shape. This was not dedicated. We can zoom into the, so these are the two nanowires, if you didn't recognize them, indium arsenide nanowires. We can zoom into the upper facet, and we see these zigzag and cubic patterns, which are the atoms, the clean atoms on the surface of these nanowires. And we, of course, can identify these facets relative to the growth direction, epitaxial growth direction of this nanowire. So in topography, everything looks great. They are pretty clean, which allows us to study their spectroscopy. So this is a parabolic 3D band structure, which comes with a quadratic density of states. However, if we will measure a 1D structure, the band structure will get quantized, like electrons in a cylinder, and the density of states will turn into a series of divergent density of states at the bottom of each quantized band called Van Hove singularities. So this is what we actually find in experiment. This is the measured spectroscopy over the nanowire, and this series of peaks is the thermally broadened Van Hove singularities that we find on the nanowire. We can enumerate them above the semiconducting gap, and we also calculated the quantized band structure of Wurtzite indium arsenide. And this is the spectrum, the quantized spectrum that is calculated. This is the density of states, which is derived from it. And it fits fairly good with what we find in experiment. And we nowadays play a bit with the diameter of these nanowires in order to get an even better quantitative agreement. So we are able to see the locations in energy of these quantized bands through the Van Hove singularities. The next question is, where are these bands? Can we visualize the actual bands and not just the von Hove singularities? For this, we do the QPI measurement that Shikun described before. This is how it goes. Electrons scatter from an impurity. They give rise to a standing wave pattern that we can then resolve in space. This interference pattern carries the wavelength of the electrons, so this allows us to extract the dispersion of the electrons. This is how it looks like when you do it on copper, when you have an isolated impurity. On the nanowires, things are more complicated. So our electrons will be in the multiple scattering regime. We will not be able to really see a single standing wave pattern, but we're hopeful that the Fourier transform analysis will be still able to extract the Fermi wavelength and the dispersion of the electrons. So we conduct the experiment over this region, and this is the differential conductant maps taken at different energies. And you see that the density of state indeed fluctuates. So the electrons are alive and they are responding to the impurities. If we look on the average density of states, we again see the von Hove singularities. This is the spectrum as we've seen before. We just flattened it by subtracting the background. So we can again enumerate the quantized bands. And of course, if we do Fourier transform, we can see the dispersing bands, 1D dispersing bands in these nanowires. So let me guide you through. Some of them are more clear, some of them are less. So there is a relative faint one at the bottom, really one that is saturated in this color scale. But now life becomes easier. So here is another parabolic band. Here is the next one. Here is another one. And here, this one is fainter, but you can still follow it. And on it goes. And here at the top, we have another very nice parabolic band. And lastly, we can compare the bottom of these bands and the von Hove singularities, and they agree. So this is an important consistency check to see that indeed the two kind of independent measurements agree with each other. So in the bulk of the nanowire, in the center of the nanowire, we're indeed able to measure the spectroscopy of the electrons. So what we did next was to take this tool to the end of the nanowire where we have the strongest.
What are those things that look like dispersing the other way, or it's?
So we know from the calculated quantized bands that it's a very complicated band structure, 1D band structure. For example, in some of these bands, it's actually multiple, like two bands, which overlap in energy, and by thermal broadening, you cannot distinguish. So, and on top of that, you have the von Hove singularity, so the density of states fluctuate. So I cannot really refer to any peak in the Fourier transform, but at the end of the nanowire, things will become clearer.
Is there evidence for Rashba, like orbit splitting?
No, to see that, you must apply a magnetic field. Right now, it's just spin up scattering to spin up and down to down, and there's no way to resolve it. So we go to the end of the nanowire. So this is the end of the nanowire. And we take a spectrum, the IDV map along this cut. And this is what we find. And we find a very rich phenomenology happening at the end of the nanowire. Of course, no superconductivity, no magnetic field applied. So let me show you what we find. First of all, we find von Hove singularities. Maybe you can dim the lights so things will look. Cameraman?
Dim the light?
Can you dim the light, please? Thank you. So we see von Hove singularities. Again, if we average the spectrum, we see them in the point spectrum. Then we see a very clear, relative to what we saw in the center, very clear standing wave pattern. And then we see these resonances, these bright and dark resonances at the very end of the nanowire. And I would try to explain what is the physics involved in these different features. Starting, and of course, this is also where the Majorana would reside once we render it superconducting and apply magnetism. So starting with this standing wave pattern that we find, if we take a Fourier transform just at the far end of the imaged region, we see, again, a very faint signature, maybe of dispersing bands. However, when we repeat, do a Fourier transform close to the end of the nanowire, we see this very strong standing wave pattern dispersing band that actually, from the energy, we know it's the lowest quantized level of the conduction band. So we can also compare it to the calculation. So this is the band structure of wurtzite indium arsenide, the bulk band structure. And this is where the quantized spectrum was calculated, the bottom of this band. And as you can see, the only fitting parameter we have here is the Fermi energy. So we can shift the spectrum up and down. And by doing this alone, we can perfectly fit the dispersion that we measure to the dispersion which is calculated. So indeed, this is the lowest quantized band of the conduction band, which for some reason gives a very strong standing wave pattern. So for a long time, we were puzzled by this. Why all other bands don't create a standing wave pattern which is as strong as the lowest one? And eventually we understood that this comes from the stability of the hot electrons that we tunnel into the nanowire. So let me explain you how this works. So we tunnel an electron somewhere into the nanowire at some high energy. It is a hot electron above the Fermi energy. When we tunnel it into in order for it to create an interference pattern, it has to travel to the scatter and back without decohering or relaxing. So it has to maintain its quantum information. However, this is a hot electron, so it can relax. If we tunnel an electron to a higher quantized band, it can very easily relax without exchanging momentum with an electron-hole pair, just exchanging energy, because it can go through interband relaxation process. So there is a very wide phase space for this process to take place. Basically, all occupied states are good candidates to exchange energy and no momentum with these excited electrons. And this follows rapidly until the electron hits the lowest quantized band, below which we have only the semiconducting gap. So once the electron gets to the lowest quantized band, it must exchange energy and momentum with the electrons in the Fermi C, below the Fermi energy. And this was analyzed by Kartig following an experiment by Barak in a different system. And basically, because of the parabolic dispersion of these bands, you cannot satisfy both energy and momentum conservation simultaneously by solely a two-body process. So instead, you excite two electron-hole pairs. You split your energy between them such that the momentum will also be conserved. So this is a three-body process with very restrictive phase space for particles to participate in. And this is why the relaxation along the lowest quantized bands is markedly slower than the relaxation along higher bands. And at the end of the day, this is why we see this lowest band giving rise to an interference pattern, which is so long relative to all other bands.
Excuse me.
Yes?
If you have this three-body relaxation, though, I would think that you would see the Rashba structure if it was there even in zero field. Because now I need momentum balance, and so I'm going to have the ability to excite scattering effectively from the other.
So the moment the electron starts to relax, I lose the interference pattern. I don't see how it relaxes down. For it to create an interference pattern, it must not relax.
So is the standing wave pattern exist near or after the Fermi energy?
Yes. I will show you. So this will come in the next slide. What this allows us, this distinction between lowest quantized bands and higher ones, allows us basically to forget about the higher quantized band in this multi-channel wire and just study the relaxation process of electrons in the lowest quantized band that we resolve very nicely in experiment. So we went back to the real space measurement. Here is this interference interfering wave again. And in order to extract it or filter out all other phenomena that happened in the end of the nanowire, we did a kind of spatial lock-in filtering. We just extract this standing wave component from the standing wave pattern. All the things that I'll show you based on this, you can actually see in the raw data, but you can see it much clearly after doing the analysis. I don't have time to go into the details of it, but I'll happily answer questions at the end. So you can immediately see that the relaxation behavior has a very non-standard behavior. Starting from low energies close to the Fermi energy and below, we have a very stable, very slowly decaying standing wave pattern. So at Fermi, you expect the interference pattern to be infinite in practice if there is no relaxation due to electron-electron interaction. Then we go to higher energies, and the interference patterns become shorter and shorter, which is sounds reasonable. The further you go from Fermi, the faster the electrons relax. But then at yet higher energies, we start to see a non-monotonic behavior of this decay of interference pattern until at the highest most energies we've measured, there is practically no decay of the interference pattern. So the electrons remain coherent throughout the window at which we measure. So where does this come from? For this, we'll have to look at the interactions and the relaxation of electrons in one dimension again. So again, the coherence length of the electrons can be written as a function of the Fermi velocity times the relaxation time or the coherence time of the electrons, which inversely is the relaxation rate, which we can estimate by the Fermi golden rule. So this gets two contributions. One is the phase space of the electron to interact with electrons in the Fermi sea, and the other is the matrix element, the strength of the Coulomb interaction via which it interacts with the Fermi sea. The phase space was calculated by Kartzig and gives some power law dependence on energy. The Coulomb interaction in one dimension is actually the interesting part in this experiment, because unlike higher dimension, it's not just the power law, it's the first modified Bessel function, which has two very distinct limits. So on very short length scales, momentum scales and energy scales, it decays logarithmically, so very slowly, but then at higher energies and momenta, it decays exponentially fast. So by summing or collecting these two contributions, multiplying them, we get the total relaxation rate, which is dominated by the phase space at low energies when the interaction decays logarithmically, but then becomes dominated by the weak Coulomb interactions at high energy and momenta. So we did get a non-monotonic behavior for the relaxation rate, with this peak somewhere around 50 millielectron volts, which is in the ballpark of what we find in experiment. So this non-monotonic relaxation behavior comes from actually the fact that Coulomb interactions in one dimension becomes exponentially small, while the phase space doesn't grow fast enough, at least over this energy span. Actually, we've seen this behavior in another setup. So we went back to the bulk of the nanowire, the center of the nanowire, where from time to time we see this series of stacking faults, topological defects. In the nanowire, you also see them in a TEM image. So these basically form quantum dots for the electrons. The electron scatters from these stacking faults and get quantized, zero-dimensional quantization this time, when we measure the local density of states versus energy and location. So we cannot do any Fourier analysis on such a quantized behavior, but what we still did was to extract the width of these resonances versus the energy at which they occur. So this is what we find. So what is energy broadening of the resonances? Where does it come from? So there are some trivial origins that we collect. One is the AC amplitude that we use in which to measure this behavior. The second is the finite temperature at which we measure. And the final contribution comes from the leakiness of these quantum dots. So how much the electrons can transmit through this stacking fault. And from the number, the residual broadening that we get at Fermi, we can extract that stacking fault reflect electrons 85% of the times they hit. So a stacking fault basically cuts the nanowire into two weakly coupled segments. So whoever is doing Majorana experiment should probably avoid having stacking faults in his nanowires. Now we're left only with the energy-dependent part of the broadening. So Again, we can think of the broadening, or this part of the broadening, as the inverse of the relaxation time. So parabolic behavior, not surprisingly, misses this behavior. But if we now simply take this curve and invert it, we get a much better agreement. We have to multiply by 3. There's a factor of 3. So actually, we get a broadening which is 3 times weaker. But the trend is the right trend. And of course, the approximation is very crude. So this is another angle of seeing this non-monotonic behavior of the relaxation coming from the broadening of the resonant peaks. So now I come to these resonances, bright and dark resonances. I have very limited time to speak about them. We actually know where they come from. So in order to see this, we took a line spectrum not till the end of the indium arsenide part, but also into the gold ball at the end of it, which catalyzes its growth. And this is what we find. So the spectrum inside the gold ball is highly quantized, which means that this gold ball is actually made of, is very dirty with indium and arsenic, and is made of lots of tiny quantum dots which are coupled to each other. And this gives rise to these very large gaps in the quantized spectrum, and to the fact that the resonances meander in energy. So this is one quantum dot, and this is a second one, and this is the transition. You see here the forking of the behavior, and the tip is not very happy when you go across them. So the gold ball is heavily quantized. And actually now we see that all the resonances that we see at the end of the nanowire are simply these resonances of the gold ball decaying or leaking into the indium arsenide nanowire. But it has a very interesting behavior, which is marked here in red. So all the resonances are actual resonances in the density of states in the spectrum, apart for these resonances that happen here below the 1D band, and where we get not just a dark resonance, but actually a negative differential conductance signal in the STM experiment. So when the STM measured the negative value, it means that you no longer measure density of states, which cannot be negative, but some other process in the tunneling process took over the usual explanation of what happens when you measure tunneling. So in order to understand a bit better what happens across this resonant negative differential conductance resonance, let me draw also the integral of the differential conductance, which is just the IV characteristics of this tunnel junction at this location. And you immediately see that this means that the total current, tunneling current that we draw from the nanowire when we cross this resonance decreases when we increase the absolute voltage. So in terms of energy, we have the resonances, and we have the 1D band of the nanowire. Whenever the tip is above the quantized resonance, we get tunneling of electrons from the whole 1D band into the tip. Once we tune the energy of the tip to be leveled with the resonance, we empty the electron from this resonant level. But this means that it doesn't, seeing this negative value or this decrease in the total current that we draw means that actually this resonance acts as a switch to the 1D band. Because it's not just that we don't draw electrons from this tip. This would just give a flat behavior, but we draw less current from the 1D quantized band once we empty the switch. So what can give rise to this very strong behavior? Somehow, of course, this resonance must interact with the 1D band. So once the electron leaves the resonance, it leaves behind the hole some positive charge, which has the flavor of what was proposed 50 years ago. Exactly this scenario, a resonance next to a continuous band. However, once you empty the resonance and leave a charge behind, all the Fermi surface needs to accommodate to this positive charge, and actually this accommodated new ground state is orthogonal to the ground state the system had when the electron was still here. So this is some kind of a very strong tool that is handed to this resonance and can indeed affect in a very extreme way the tunneling that we collect from the 1D band. But this is just speculation at this level. We don't know really, we don't have a full model for this behavior. So with this, I'll just maybe skip the summary and mainly thank the people. So Jonathan Reiner and Rita Avraham have led this experiment, and this is the rest of the group that contributed in running it. The nanowires were grown by Hadass Strickman. Calculation modeling was done by Ion Kosma and Binghai. And for the theory part, we had a very fruitful discussions with Marissa and Felix, and we enjoy lots of discussion within the department and funding for different agencies. Thank you.
Question.
So you show the quantization of the gold particle and the end of the indium particle white. So look like that's very interesting the result. We don't see you say this quantized level in the gold or
I agree.
the special part of your particle.
I agree. So we have lots of gold around. Our substrate is also a gold substrate. On the gold substrate, there is no quantization, but it surprised us in the beginning also, but this gold droplet at the end of the nanowire is really what incubates the growth. So it's full with indium and arsenic. And there is not much measurement to compare to what is really the electronic state in this gold ball, but two of the behavior that we see.
Maybe indium droplet. Maybe.
No, so it's still. I mean, we did look at it in TEM, and so it's mainly gold, but it's a very dirty piece of gold. And what kind of maybe phase separation? What's the chemistry inside this gold droplet? We don't know. We just see that the quantization is just too large to be coming just from the size of the droplet, by orders of magnitude.
Is the Coulomb interaction for the relaxation in one dimension?
No, so it's the three-dimensional Coulomb interaction with the cutoff that comes from the diameter of the nanowire.
Okay, we should move on. So let's thank again.